Today's lecture is lecture 33, chapter 11.1 to 11.4 on solutions and solubility. So far this semester, we've only considered solutions consisting of pure substances. But in reality, a lot of conditions we're dealing with mixtures. And so mixtures are defined as any combination of two or more pure substances blended together in some arbitrary proportion without chemically changing the individual substances themselves. So we can have two different types of mixtures. Heterogeneous or heterogeneous mixtures, where the components are visually non-uniform, so such as if you mix salt together in oil, they don't dissolve together and you can see the two different states of matter in that heterogeneous mixture. Or it could be homogeneous or homogeneous, which is the mixing is uniform. So there's no visual difference between the individual components. So example of some homogeneous mixtures are seawater, where you have salt dissolved in water, or if you're talking about brass, which is two different metals, copper and zinc together. So with these mixtures, the important thing to note is that you're not actually physically changing the materials, the chemical makeup of the individual materials that you're mixing together. You're only just, the word, mixing them together. So homogeneous mixtures can be classified according to the size of their constituent particles. So we have three different types of homogeneous mixtures depending on those sizes. So a solution is defined as a mixture that contains particles with diameters in the range of 0.1 to 2 nanometers, which is the size of a typical ion or small molecule. And so for these, you cannot actually physically see the individual particles within the solution. So think about, for these guys, you're thinking about aqueous sort of solutions that we deal with in the lab. You cannot actually see, say, think about a copper sulfate solution. You can't actually see the copper 2+ ions or the SO4 2- sulfate ions in solution. All you can see is sort of a homogeneous mixture. The next mixture is a colloid, which is a mixture that contains larger particles with diameters in the range of 2 to 500 nanometers. And so these solutions are often murky or opaque. And so some examples of colloids are milk, or in gas state, we're talking about fog. And so if you take a look at the milk that's in your refrigerator, you can't actually pull apart those individual components to there. It's suspended in there as colloid particles the proteins are large enough in there that it looks like a murky or opaque substance. And finally, we have suspensions, which are mixtures that contain even larger particles than colloids. And so these are not actually truly homogeneous. They can separate out upon standing, and they are visible by low power microscope. So examples here are blood, paint, and aerosol sprays. So if you put a microscope slide of blood down and you take a look, you can actually see the individual components of that blood, the red blood cells and the plasma and any other sort of cells that are in there. And so this is actually a suspension that could actually separate out different than the solution or the colloid mixtures that are not going to separate. So we have several different kinds of solutions that we can deal with. So you can have gas mixtures in gas and gas mixing together. Example of that is air. You can have gas and liquid mixed together. So for example of that is carbonated water or soda. Gas and a solid together. For example, you could put hydrogen gas in palladium metal. You can mix two liquids together. For example, gasoline. Liquid and a solid. So dental amalgam, which is mercury and silver, you'll use for dental implants. Solid and liquid, that would be an example of seawater. And solid would be an example of a metal alloy. So any sort of mixture, this shows that any sort of combination of our different states of matter can actually mix together. So solutions are composed of solvents and solutes. And so the definition provided by your book for solvent and solute are pretty unsatisfactory, really, if you ask me. Their definitions are the solvent is the major component, the solute is a minor component. So in parentheses here, I put the definition that I think is much more useful. The solvent is the material or the substance that you are dissolving into, and the solute is the substance that you are dissolving. So if we think about mixing a solution of salt water, you're going to be putting powder or crystalline salt into water. So the water itself would be the solvent, the substance that you are dissolving into. The solute, the substance that you're dissolving, would be that crystalline salt. And so we have a saying when we're talking about solubility and dissolving substances that like dissolves like. So if the chemical structure or the chemical properties of a solvent and a solute are similar to one another, they will dissolve. If the chemical properties are different from each other, then they are likely not to dissolve. Okay, so if you talk about having a polar solvent, that will most likely dissolve a polar solute. If you have a nonpolar solvent, it's unlikely to dissolve a polar solute, and vice versa. So if we take a look at the dissolving of a crystalline salt in water, the dissolving happens due to the intermolecular force interaction between our polar water molecules and the ions in our crystal lattice. And so you can see here, this is an ion-dipole interaction where the intermolecular force caused by the surrounding, the hydration of these ions by these water molecules is stronger than the intermolecular forces of the Coulombic interaction holding together our positive and negatively charged ions in the crystal lattice. So these intermolecular forces cause between the polar water molecules and the ion, those stronger intermolecular forces make it more energetically favorable to be in the dissolved, hydrated form than it is to be together in the crystal lattice form. And so when we're talking about solubility rules for salts that do not end up dissolving in water solution, those are materials that the energetics are stronger where to keep it together in the crystal lattice form than it would be to be hydrated by water. So whichever energetic situation is going to be stronger is the situation that's going to exist. So if there is more energy released caused by the hydration, it's going to dissolve. If there's more energy released by staying in a crystal lattice form, then the solution is not going to dissolve and it'll stay insoluble. And so we can think about this of dissolving a solution in terms of energetics, where we have an energy diagram here, where we start off on our base level here. So this should sort of remind us of our Born-Haber cycle, the energy diagram associated with the formation of salts. If we start off in the separation where our solute and solvent are separate from one another, the energetics of them separate from each other, and then on the bottom would be the energetics of the solution together. So if the energy associated with keeping the solvent together and keeping the solute together, the summation of those two energies is smaller than the energy released upon the formation of the solvent-solute combination, then you're going to end up having a solution dissolve. So if the net energy is released. Whereas if the summation of the energies keeping the solvent and the solute together are greater than the energy released when the solvent and solute form together, so we see a net energy input, then you're going to have an insoluble species. So all of these movements in chemistry have to do with the energetics. If dissolving causes a more energy efficient situation, then you're likely to dissolve. If the energetics support a non-dissolved species, if the energy is not going to be released, then you're going to see that the status quo will remain and there will be unlikely situation to dissolve. So we can continue to add a solute into a solvent and keep dissolving more and more and more until we reach what's called a saturated solution. So a saturated solution is a solution containing the maximum possible amount of dissolved solution at equilibrium. So if you think about having a saltwater solution, so if you have a cup of water at your house and you keep adding salt or sugar to that solution, you can keep mixing it and it'll keep dissolving until it reaches a certain point. At that individual point now, no more of that salt or sugar would be able to dissolve in the solution. You've reached the saturation point of the solution, such that if you added any more of that salt, it would not dissolve and it would stay on the bottom of the solution as a salt crystal. And so at this point where we're totally saturated, we consider that we are at an equilibrium between the dissolved solution and our solute and solvent being separated. And so there's such a thing that's called a supersaturated solution, which is a solution containing a greater than equilibrium amount of the solute. So this has typically happened by changing the temperature of your solution. So we will take a look in the next slide actually. If you increase the temperature of a solution, so here we'll actually just jump to the next slide. If we increase the temperature of a solution, so temperature on the x-axis, solubility on the y-axis, we can see from many different materials here, if we increase the temperature of the solution, you will increase the solubility of a material or a solubility of a substance. Okay, so if you want to make a supersaturated solution, which is a solution that contains greater than equilibrium amount of solute, typically you would increase the temperature of the solution such that you can dissolve more of the solute into the solvent, and then you will slowly bring that temperature back down again. And if you do that at a slow enough, controlled enough environment, you can actually create a supersaturated solution where you have more dissolved solution than would be expected by the equilibrium. And so an interesting thought or an interesting sort of component about supersaturated solution, if you add one single, what's called a seed crystal, into this supersaturated solution, you can see all of that extra crystals of the solute that should not, by theory, be dissolved within that solution will immediately drop out as these beautiful looking crystalline structures. Okay, so make sure that you remember here that as we increase temperature, we increase solubility. And if we take a look at gases actually have an opposite. So that was the effect of increasing temperature, increases solubility. This is for liquids typically. If we take a look at the effect of temperature on gases, so talking about gases becoming soluble in water, we see an opposite trend actually, where we see as we increase the temperature, we can see a decrease in the solubility of gas within water. So this is actually very interesting when we think about the solubility of oxygen within water. So if you think about bodies of water out in nature, and so lakes, rivers, and streams. So we know that we have lots of wildlife that lives within these bodies of water. And so these fish and wildlife require oxygen dissolved in the water in order for them to thrive and survive. And so that oxygen, that O2 oxygen gas, is dissolved in the water. But so we're seeing a situation here where global warming is occurring, and we're seeing our global temperatures are beginning to rise. And so as our temperature of the Earth begins to rise, we can see that the solubility of oxygen within the water is actually decreasing. And so this is becoming quite a devastating situation, actually, where we are changing the chemistry of the water. And this is having adverse effects on the wildlife that are living in the water, as well as the plant life that depend on oxygen dissolved in the water to be able to survive. So this temperature dependence of solubility is really, really important in lots of different aspects of life. So we can also see that the pressure that you apply to a closed system also affects solubility as well. So we talked about the vapor pressure as being an equilibrium between the amount of material that's in the gas phase versus the amount of material that is in a liquid phase. And there's an equilibrium at every given temperature between the gas phase and the liquid phase. And so that vapor pressure is has an equilibrium at a given external pressure. So if we have a closed vessel attached to a piston, that we can change the total pressure of this headspace. If we increase the external pressure on this headspace, what that's going to do is drive some of the molecules. It'll increase the pressure in this headspace region, and that will drive some of these gaseous molecules back into our liquid solution. And then so eventually a new equilibrium will form between the liquid phase and the gas phase, and that will be a brand new vapor pressure. Okay, so it's important to know that solubility can depend on both temperature and on pressure. So let's take a look of an example of solubility. So this goes back to our statement at the beginning of our discussion of solubility that like dissolves like, and unlike substances are not going to dissolve. So remember I told you that polar molecules will be dissolved in polar solvents. Nonpolar molecules will be dissolved in nonpolar solvents. Okay? And so polar solvents are unlikely to dissolve nonpolar solutes, and nonpolar solvents are unlikely to dissolve polar solutes. So given that idea, we ask the question, pentane, which is C5H12, and 1-butanol, which is C4H9OH, are organic liquids with similar molecular masses, but substantially different solubility behavior. Which of the two would you expect to be more soluble in water? And explain. So pause the video for a moment and consider this example. Okay, so we expect that 1-butanol, down here on the bottom, we expect that to be soluble in water, whereas we do not expect pentane to be soluble in water. So the reasoning behind this is, we can see that 1-butanol, having this OH group, makes this a polar molecule, with a dipole moment going in the direction of this OH, whereas pentane is a nonpolar molecule. And so we know that H2O, water, is a polar solvent. So therefore, like dissolves like, 1-butanol will likely dissolve in our polar water because it is in itself polar. Whereas pentane will not dissolve in water because it is nonpolar and water is polar. All right, that's it for the day. Thanks for your time.